In this lecture, we are going to study about constant strain triangles. It is a two-dimensional problem. So when we are given a body like this, okay, and we have two dimensions. It's a plane body, so x and y. That means there will be two displacements as well. In the x direction, let us consider u, and in the y direction it will be v. So if you are talking about body force, again we will have in terms of the components in terms of x and fx and fy. Also, any point force will be represented by its two components px and py. Let this be the cross-sectional area of the body, capital A, and we have a traction force which is acting along the surface of the body, denoted by capital T. So in 2D problems, the displacement, the traction force and the distributed force, body force, are functions of position which are indicated by x and y. So as I've said before, the displacement vector u will be given by u and v transpose. U and v we know are the x and y components of the displacement respectively. The stress and strain is given by sigma is the stress. So we will have direct stress sigma x, direct stress sigma y, and tau xy, which is the shear stress transpose. And the strain epsilon is given by epsilon x, epsilon y, gamma xy transpose. The body force is given by F equals to Fx, Fy transpose. The traction force is again given by its two components Tx and Ty. The elemental volume is given by dV equals to T into dA, where T is the thickness. At any point x, y. The body force has units of force per unit volume. The traction force has units of force per unit area. The strain displacement relationship is given by epsilon equals to dou u by dou x, dou v by dou y, and dou u by dou y plus dou v by dou x transpose. The stresses and strains we know are related by sigma equals to Young's modulus into the strain epsilon. Now how do we carry out the finite element modeling of this given figure to us? Okay, so this was our body which we were given, two-dimensional region, and we have to divide it into straight-sided triangles. So we had a traction force here, and some part of the body was fixed. So we have to divide this into smaller triangles like this. We have to represent the given a two-dimensional body as much as possible by this triangles. So here I have divided the given two-dimensional region into a number of triangles. So this is how I'm going to label it: 1, 2, 3, and so on. So these are the elements. We have 1, 2, 3, and for the node numbers I will just be numbering them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This notation for the degrees of freedom is going to be given like this. So if we have a node I, the degrees of freedom are going to be represented by 2i minus 1 and q2i. So for node 1, for example, if we have node 1, 2 into I is 1, minus 1 is 1, so this will be q1, and 2i is 2 into 1, which is 2, so this degree of freedom will be q2. So for node 1 it will be q1 and q2. Similarly for node 2 it will be q3 and q4, and so on for all the nodes. So this is the denotation we are going to use for constant strain triangles. It's similar to the ones that we have used in trusses. So after the two-dimensional body is divided into straight-sided triangles, the point where the corners of the triangles meet are called as nodes, and they are numbered as nodes. Each triangle is formed by 3 nodes and 3 sides and is called an element. So the ones that I have circled here, say for example 1, 2 and 3, these are elements, whereas the ones that I have marked in blue are nodes. The elements fill the entire region except small regions at the boundary, because the region that we have considered is circular in nature and we are trying to represent it using straight-sided triangles. So like when we see here, there are small portions which could not be covered because we are considering straight-sided triangles. Okay, so that is why we say that FEM is a representation, or the solution that we get from FEM is approximate. Okay, it is not the exact solution. So these unfilled regions exist for curved boundaries, and it can be reduced by choosing smaller elements or elements with curved boundaries. Okay, but here we are studying constant strain triangles, so we are considering straight-sided boundaries. In the two-dimensional problem, each node is permitted to displace in 2 directions, that is x and y, and therefore each node has 2 degrees of freedom. The global displacement vector of the body will be given by capital Q equals to Q1, Q2, Q3 and so on, where n is the number of degree of freedom. Okay, so let us consider one of these triangles. Okay, we are considering one of the triangles and we have nodes 1, 2 and say 3. Now or let me consider this element 1, and it has nodes 1, 2 and 7. Okay, this is element 1. Now since it's a two-dimensional body that we are considering, each one will have 2 degrees of freedom. So this, for example, will be Q3, Q4. This will be Q1, Q2, and this will be Q13 and Q14. So number of nodes 3. The degree of freedom of each node is 2. Therefore, degree of freedom of the element 1 will be 3 nodes multiplied by the degree of freedom of each. So the degree of freedom of the triangle is 6. This is only of the triangle, but if we see of the body as a whole, okay, we need to multiply the number of elements. Okay, so if we go ahead and number all these elements, so we have 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13 elements. The degree of freedom of the entire region would be 13 into 6. Okay, so this would be of the entire body, whereas this here was of only one element. Most standard finite element codes, they use the convention of going around the counterclockwise direction. Okay, so here in this body, if we see, I have labeled it anti-clockwise. So this is the first node, second node and the third node. That means it is going in this direction. Okay, the displacement components of a local node will be given by small q 2i minus 1 and q 2i. Okay, so you have a node I. So in the local nodes it is given by these two. The element displacement vector is given by q equals to q1, q2, q3, q4, q5 and q6 transpose. In the next lecture we will be learning about how a displacement of a point inside the element has to be represented. So this is all for this lecture. Thank you.